Hello, everyone. Thanks for coming today. We have today uh, Franz Ciceri, who I had the pleasure to work with at Max Planck Institute in Potsdam. And he will talk about the recent papers that he has been working on in the last few years related to dimensional reductions of supergravities. Please, Franz, take the floor.
Thanks a lot. Thanks for inviting me. Yeah, so as you say, I'm going to talk about Kaluza-Klein truncations of supergravities, especially to two-dimensional supergravities. And I'm going to try to summarize a rather long story that resulted in the following papers in collaboration with Guillaume Bossard, Gianluca Inverso, and Ciceri and Henning Zamkleben. It's going to be about two-dimensional gravity. And as you probably noticed during these last few years, people have looked a lot at these two-dimensional gravity models. And I think one of the main reasons is that they are usually simpler than gravity in higher dimensions. For instance, if you just write the Einstein-Hilbert action, it boils down to total derivative. So the simplest non-trivial models that people could, have been looking at are these dilatant gravity models where the two-dimensional Ricci scalar is multiplied by a dilatant field called rho, and where you can optionally have also a scalar potential for this dilatant field. And in particular, a quite famous model that has been looked at a lot is this Jackie-Teitelbaum model, where the potential is linear in the dilatant. So although these models are simple, they still have some interesting properties, and this is because d equal 2 space-time dimensions is the lowest possible dimension for which you still have a notion of Riemann curvature. It's also the lowest possible dimension for which you have a light cone, so you can have black hole solution. And furthermore, it's also the case where your space-time have boundaries with dynamics. So there is also possibility of studying ADS CFT or more generally holography. But what I want to do in this talk is I want to talk about different kinds of models which turn out to be much harder to study than in higher dimensions. And I'm going to be interested in the maximally supersymmetric two-dimensional supergravities. And in particular, those that arise from flux compactifications of string theory in between quote. By this, I mean flux compactifications of 10 or 11 dimensional supergravity. And the long-term goal of this whole program is to be able to rigorously study this holographic duality between string theory and supersymmetric ADS to background and certain one-dimensional supersymmetric field theories or matrix quantum mechanics. I'll say a bit more about this later on. So since I'm guessing most people are not very familiar with these maximal supergravities, let me try to give a large overview of the different maximal supergravities that exist in different dimensions and talk a bit about their properties. So it starts in 11 dimension where you have, let's call it here M theory in between quotes. So you have one theory, which is the low energy limit of the elusive M theory. In 10 dimensions, you have two maximal supergravities, which are called type 2a or type 2b, in which differ by the chirality of their fermions. And what happens is that if you put this higher dimensional series in 11 or 10 dimension and you reduce them, you can do a Kaluza-Klein reduction on a torus of appropriate dimension. You generate a whole series of maximal supergravities, which are called ungauged supergravities. And there is a unique one in each dimension. So there's just one in 5. There's a single one in 4, which is quite famous, called incorrect supergravity. 1 in 3, sorry. And finally, when you get to 2, you get to the single ungauged supergravity in 2 dimensions, which consists of a nonlinear sigma model coupled to dilatant gravity with very specific, it's a very specific models with certain peculiar properties. And this model, it's been studied already a long time ago by the following people. And one of the reasons why it's so special, it has to do with the rigid symmetries of these different engaged supergravities. And so in each dimension, there are surprisingly large rigid symmetries, which are based on exceptional Lie groups. So in 5 dimensions, the series invariant on the a Lie group E6, in 4-dimension E7, 3-dimension E8. This is all known for a long time. And when you get to 2-dimension, there is a way to show that the field equation of your theory admits an infinite number of conserved charges, which generate an infinite dimensional group, which is an affine group. And for the moment, I'll just call it E9. And as a result, the theory is integrable, at least classically. So this is for the 2-dimensional ungauged supergravity with maximal supersymmetry. So in contrast with these ungauged supergravities, you have what's called gauged supergravities in each dimensions, and you have a whole set of them. And the way to obtain them is to actually select a subgroup of your rigid symmetry and to promote it to a local invariance of the theory. So you essentially gauge a subgroup. Depending on which gauging you choose, you get a different theory. And these are, in a way, the juicy ones, if you want, because in these ones, the scalar fields that were already present in the ungauged supergravities, they develop a scalar potential, and this means that these gauged supergravities, they can have interesting solutions such as ATS, de Sitter, anti-de Sitter, or so on. So there is a universal way of describing gauged supergravities in each dimension in terms of universal Lagrangian, which is based on the notion of an embedding tensor, which is essentially a tensor that encodes which subgroup of the rigid symmetry you have turned into a local invariance of your theory. So obviously, you cannot gauge every subgroup and get a consistent gauge supergravity. So there are certain restrictions on which gaugings you can pick, and this translates into certain algebraic constraint on this so-called embedding tensor. I'll say a bit more about this later on as well. So this is a story which happens in every dimension. So if I take probably the most famous example, it would be in 4-dimension. Turns out that you can consistently pick an SO8 subgroup of this E7 exceptional Lie group, and you can gauge it. And this leads you to this SO8 gauge supergravity, which has been constructed in the 1980s. And there's another property of this theory, which is that you can also obtain it directly from 11-dimension by reducing not on a torus, but on a 7th sphere. So this is a Kaluza-Klein truncation on the 7th sphere that leads you to the SO8 gauge supergravity. What does it mean? It means that you compactify your 11-dimensional theory on the 7th sphere, and then you throw away essentially an infinite number of massive Kaluza-Klein modes. And this is something that is highly non-trivial, that you can actually throw away all these modes without creating any inconsistencies in your theory. This is something you can always do on the torus. There are some group theory arguments that tells you that the truncation is always consistent of the massive mode, but on sphere, it's a much more complicated problem to prove. So in practice, what you have to do if you want to prove the consistency of this truncation in the sphere, you have to take your 11-dimensional theory, and you have to specify an ansatz for all the fields of your 11-dimensional theory in which you describe their dependence on the internal coordinates in terms of geometric quantities of the sphere. You have to plug this ansatz into the field equation, and then you have to show that all the internal coordinate dependence factorizes out of the field equation, leaving the field equation of the lower dimensional gauge supergravity. But of course, since the theory is very highly nonlinear to start with, in practice, it's a very complicated task to prove that it works. And there are only a few cases, in fact, that we know work out. So by that, I mean that there are many gauge supergravities, but only a few of them arise from consistent truncations of higher dimensional theories. So,
does it mean that only a few of them arise in the known way, or it is proven that some cannot arise from such truncations?
It's proven there are, for some of them, it's proven that they cannot admit a higher dimensional origin in terms of consistent truncation. Yeah. So, I mean, you could ask, okay, you know, now it follows from a consistent truncation on the 7th sphere. What does it buy you, this consistent Kaluza-Klein truncation? Well, by definitions, if you have a consistent embedding in higher dimension, it means that any solution of your field equations in lower dimension, essentially you can use the embedding to uplift it to a configuration in 11 or 10 dimension, And this will be automatically a solution of your higher dimensional series. So it's a powerful embedding if you want. It's also very useful for holography, because it means that, for instance, if you have an ADS solution here, which uplifts to some solution 11-dimensional supergravity, well, you know that the dual field theory, which describes essentially the fluctuations around this ADS background, for the dual field theory, if you have a consistent truncation on the gravity size, it means that you have a set of gauge invariant operators which are closed on the operator product expansion. And it also means that if you want to compute correlation functions of these operators, you can essentially only study the fluctuations around the lower dimensional series and not around the full 11-dimensional series around the background. So it's a strong tool. So essentially, as I said, there are not so many known cases of consistent truncations to maximal gauge supergravities. And in fact, the most famous ones are ones on spheres. So I listed them here. There are only 3. The first one is from 11D on S7. You go to 4D and you get this SO8 gauge supergravity. It has an ADS4 solution, which uplifts to ADS4 cross S7. And the fluctuations around the supergravity fluctuations around this background, it's known to be holographically describing the dynamics of M2 branes. So there is a 3-dimensional superconformal theory known as ABGM, which is the holographic dual. There is another example where you take 11-dimensional supergravity, you reduce it on S4. There is a solution associated, which is ADS7 cross S4. In this case, the brane dynamics, which is dual, is the M5 brane. And in this case, the superconformal series, the 2,0 superconformal series in 6 dimensions. And finally, there is the famous one, which is 2D supergravity on the 5-sphere. There is ADS5 cross S5s, and the dual series is an equal for superyoungmans, describing the dynamics of these branes. So you might ask, okay, now if you consider the case of 2 dimension, would there be some new example which would have a famous superconformal field theory on the other side? Anyway, so all I've said so far was really for all dimensions up until 3. So now what happens in 2? Well, in 2, you can try to play the same thing.
Can I ask about the left side in 2? So an ungaged thing, this E9 is just affine E8, so some kind of loop group with a central extension of E9.
It contains the affine extension of the loop group over E8, but a bit more stuff in fact, but it's essentially that, yeah.
Okay, and then it has a level, I guess? I mean, it should have a central charge corresponding to
the specific level. And, yeah.
Oh, okay, so what's the level? I mean, is it an integer?
Yes. Yeah. It's I mean, what do you mean the level? I mean, like the fields transform in specific highest weight representation, which corresponds to a certain level of the affine. I mean,
yeah. So right. So when you have the commutator of what is it, like J, K, and J minus K at opposite things, there's a central charge term in the algebra.
Yeah, it's fixed to a certain value. Yeah, in the representation that the fields will be transforming on.
Okay, so if it's an integer and positive, that means it's a unitary, no? So it's integer and positive, this number, or I mean,
it's integer and positive. I mean, okay, I'll get to it, but yes, I'll get to it. I'll show the fluctuation relations, and you'll see it. Yeah.
Okay, very good. Thanks.
Yeah. So in 2 dimension, the story doesn't quite work, because if you start from the ungauged model, which has this affine symmetry 9, and you try to gauge subgroup of it, you run into some troubles. Especially you run into some troubles when you try to construct the scalar potential of the associated gauge supergravities. And the reason, which I don't want to really get into, is that the scalar potential is fixed usually by supersymmetry. And having supersymmetry in 2 dimensions in the presence of gauge couplings is a long-standing issue, which boils down to a problem of representation theory of this group E9, or rather its maximal unitary subgroup. And it's something that is not known even at the mathematical level, and that's why people have never really been able to construct these 2-dimensional gauge supergravities straight in 2 dimensions. So the alternative is to come from higher dimension and derive a subset of them, the subset that comes from Kaluza-Klein truncation. And that's what we did, and that's what I will discuss. But as I said, actually writing down ansatze of the higher dimensional series such that you have a consistent Kaluza-Klein truncation is very hard. The ansatze are highly nonlinear. So what is used in these modern days is a reformulation of the higher dimensional series, which is known as exceptional field theory. So there's a dictionary between this reformulation and the original series. The dictionary is very complicated, but they are completely equivalent. But this reformulation is such that now it very much looks like already a theory in 2 dimensions, such that if you want to write down a truncation ansatz which is consistent to 2 dimensions, it takes a very simple form and it becomes very simple to actually prove that it's consistent. Of course, I mean, if you want to re-express your ansatz in terms of the original fields, you have to plug in the dictionary between the 2 formulations, and then you recover the ansatz, which is really ugly. But the proof of the consistency of the truncation becomes very simple if you use this reformulation. So what are the results we got? There are 2 results, essentially. So first of all, we constructed this reformulation, and we studied some very general truncation, which are known as general structural truncation to 2 dimensions. And we were able in this way to construct the full dynamics of all 2-dimensional maximal gauge supergravities that admit a consistent embedding in 10 or 11 dimensions. So I'll present the full dynamics later on in the talk. And then we worked out a specific example. We explicitly constructed the ansatz, which corresponds to a reduction on the 8th sphere starting from type 3 supergravity, and which leads to a specific gauge supergravity in 2 dimensions, which is SO9 gauge supergravity. So SO9 is the structure root of S8 here. And so this has also some nice interpretation in this holographic setup, because it contains an SO9 invariant domain wall solution. So it's not quite ADS2, but it's ADS2 with a non-constant dilaton. And this domain wall uplifts to 10 dimensions to a warped ADS2 cross S8, and fluctuations around this model, they describe this time the dynamics of D0 brane. So this means essentially that the holographic dual in terms of field theory is this BFSS model of supermembrane that was put forward a long time ago. In fact, has a non-perturbative definition of MCM. So having the consistent truncation on S8 to SO9 gauge supergravity, I mean, is a very strong tool to actually study this BFSS model with holographic techniques. But I'm not going to talk too much about this example because I don't think I'll have time. So I will the plan is mostly this. So I'll talk about the engaged model in D equal 2. I'll motivate it by coming from 3D. I'll try to gauge it and obtain as much as I can of the gauge dynamics, but I won't be able to get the potential, as I said. Then I'll say a few words about this exceptional field theory and the reduction, and then I'll present the full gauge dynamics at the very end of the talk. And I think I conclude there. Okay. Any question?
Can one derive the same from like 11-dimensional supergravity in some reduction, like on S9 or something? Or is it?
No, exactly. So, I mean, since 2A supergravity, you can always uplift it on a circle to 11 dimension. Because you have a consistent truncation from 2A on S8, for sure you can write a consistent truncation of 11D on S8 cross S1. But it's not like a Hawk vibration or anything. It doesn't combine into an S9. But S8 cross S1, yes, works.
I mean, is it a theorem that you cannot do, or it's just not known if it's possible?
No, you can do. I mean, there is an uplift to 11D with an extra circle.
No, but if you want to do S9.
I know S9. It's. I think there should be a way to prove it based on some group theory argument, because the embedding tensor that specifies the gaugings has to satisfy certain constraints, and they probably will be in tension with the gauge group you would get from the 9th sphere, which would be SO10. But I'm not sure, but I expect that it will definitely not work.
In the other cases where it does work, there's some sort of flux which protects you and makes it work. That's why it's always for a stack of M2 branes or a stack of M5 branes. But there's no flux, which would be the right dimension for an S9.
Yeah, there's also
So I
that.
think that's why.
Yeah, I mean, indeed, on the SH, you have the F-form flux, which is the dual of the two-form flux in 2A, and that makes it work. Yeah, but you're thinking about conformal branes. So here it's a bit different, but so I don't know if it's really a no-go.
Right. But here, so you're should I think of this as a near horizon geometry of a stack of D0 branes in type 2A?
Yeah. It's exactly that.
Okay, so when you say it's S8 times S1, it's S1, but with a lot of momentum around the S1 direction. I mean, it's not really a trivial S1.
No, it's not a trivial S1.
These
And
D0s,
the uplift
right?
in 11D is a PP wave. It's a pure solution. Yeah.
Okay.
Yeah. Okay, so let me spend a bit of time on the engaged part here. So let me start in 3 dimensions and see where we get. So 3 dimensions. Why do I start there? Because it's a bit less weird than 2. But nevertheless, you might not be familiar with the 3-dimensional Lagrangian. So it has 2 terms. It's pretty simple. It's just the 3-dimensional Ricci scalar with the determinant of the metric in front. And then there are scalar fields, 128 of scalar fields that parameterize a coset space, which is E8 over SO16. And so in the Lagrangian, you have the standard kinetic term for sigma model for the E8 over SO16 coset space. So this current here, P mu, is the Moer-Cartan form projected on the compact part. So if you decompose it along SO16 and the non-compact, you find the P. So this is rather standard, and of course, by definition, the 3-dimensional Lagrangian has a rigid E8 symmetry, which is the one of the sigma model. So now, as I said, you can just go down to the 2-dimensional theory by putting the theory on a circle. So that's what you're going to do. You can use the 3-dimensional Lorentz symmetry to do your standard Kaluza-Klein reduction. So you fix your dry bind into this upper triangular form with the Lorentz symmetry. You have the 2-dimensional, you have the tri-bind. You have one scalar field, which is essentially the size of your circle, which is I call it the dilaton, and you have a single vector field. And then you perform a reduction. So you declare that all your fields are independent of x3, which is here the coordinate of the circle. If you substitute the ansatz into your Lagrangian, you end up on this. You get just the 2-dimensional Ricci scalar. You get a term, Maxwell term for the graviphoton A mu. And then you get the exact same E8 over SO16 sigma model, which relies on the coset space parameterized by the 128 physical scalars that you started from.
Is this the compact E8 or is it E8, 8 or one of these?
Yeah, it's mostly it's the maximally non-compact version of E8. So 70 non-compact generators and no, what am I saying? It's the maximally non-compact. Yeah.
Okay.
It's E8-8. Yeah. And there is this power in front of the whole thing of the dilaton, and I mean this is of course playing a huge role. It's the most important dilaton of your life at the moment. So. You could say, I mean, usually you can remove this type of dilaton by doing a virus scaling of your psi-bind. But in 2 dimension, of course, this virus scaling, they compensate between the Ricci scalar and the determinant. So you cannot remove the dilaton, it's there, it sticks. So you can eliminate, you can integrate out the vector field. You can set this term to 0. You can integrate them out modulo a constant of integration, which I set to 0 for here. And then you're just left essentially with this Lagrangian, where I decided to go to conformal gauge, meaning that my psi-bind, I fixed it to be completely diagonal, and I just extract the conformal factor, which I call sigma. And in this case, the 2-dimensional Lagrangian for engaged supergravity boils down to these 2 terms. So d mu d sigma, no, d mu sigma, d mu rho, and then the kinetic term for the sigma model with a rho factor in front. So you can look again at the Lagrangian, and then you say, okay, sure, I still have the rigid E8 symmetry. You also notice that you have the variable scaling as a symmetry. I mean, you had it from the start. So this means that you can shift sigma by constant values. And then you might ask, okay, where is the infinite dimensional symmetry? And although I'm not going to prove exactly that there is one, but in order to see it appearing, you have to go on shell, you have to look at the field equations. This is typical for supergravities in even dimensions. You see the full symmetry group, rigid symmetry of the theory when you go only on shell. Well, to be debated with certain people. And so let me look at the field equation. So there is the field equation for the field rho. So the field rho is just a free field. So you get box rho is equal to 0. Which you can interpret as the conservation of a current. And you can, in this case, dualize the field rho by introducing a dual field, which I call rho tilde. And the integrability condition for this duality equation, meaning here, if I contract with d mu, both sides are 0 because the integrability condition boils down to the original field equation for the field rho. So that's the standard way of introducing dual fields on shell. In even dimension, not in even dimension, but in even dimension. You can do the same now, but for the coset scalars. So for the 128 scalar fields that parameterize the E8 over SO16. In this case, the field equation takes the following form. So again, here you have a fractal rho inside, and that makes the whole model very non-trivial. You can interpret it as the conservation of the charge. And then you can introduce the first set of dual scalars, which I call here Y1, and which are valued in the E8 algebra, which are related to the original physical E8 scalars as follows. And again, the integrability condition of this duality equation boils down to the original field equation for the E8 scalars. Now, I mean, this is not a proof, but it turns out that there is an infinite number of such conserved charges that you can define in this system. And so this means that you can introduce an infinite number of such dual scalar fields, which I call Yn, such that the integrability condition for this whole system of nonlinear duality relation is given by the conservation of the current. And this means that the whole consistency of the towers essentially relies on the field equations of your original physical scalar fields. So you might then ask, okay, now you have introduced on shell an infinite number of scalar fields. There is this kind of nonlinearity in the sigma model sector, which is also due to the field that rho that appears here. You might ask now, what is the symmetries, the rigid symmetries of this system? So what are the on-shell symmetries? Well, it turns out that you have a couple of more. So particular for rho tilde, which is the dual to the dilaton, you see that you can shift it by a constant value. And of course, that won't change the system of equation. And you have such shift symmetries essentially for also all the infinite number of dual potentials Yn. And you can always shift them by essentially constant element of the E8 algebras. And you have also a whole set of non-linearly realized so-called hidden symmetries that act on this system. And if you combine the two, something that, of course, I cannot prove here, they form what's called the loop group over the over E8. So now if you take all the symmetries I presented, they combine into what I announced before. They combine on shell, the symmetries of the theory, into this affine group, which I call E9, which includes the E8 loop group, which also includes the Weyl scaling of the conformal factor, as well as other symmetries, the non-linearly realized ones, and so on. And then you also have a semi-direct product with shift symmetries shifting the field rho tilde. So at this point, this is the full on-shell symmetry of the theory. And you can nicely describe the way this symmetry acts on this infinite number of fields by realizing that the scalar fields that I have introduced on shell now parameterize the coset space, which is infinite dimensional, which is E9 times Rn-1 divided by the maximal unitary subgroup of E9, which is a strange beast that I call E9. I don't want to go more into details about this strange group. Okay, so if you want to keep on going, of course, you would like to work with this infinite number of fields on which the affine symmetry is realized. And you would like to have a nice way to encode all of these duality relations. And here, essentially, there are two possibilities. The first one is to use a generating function. I mean, this is old work from Belinsky, Zakharov, in Brighton-Leonard Mason, known as the linear system. But that's not at all the direction I'm going to take here. You can do something which is completely equivalent. Here, I'm skipping a very long story. But to encode all these duality relations, you can use a twisted self-duality equation. And however, what you have to do is that you have to enlarge, to use this twisted self-duality equation, the group theoretical structure. So instead of having the coset space E9 times the shift symmetry is RL-1, you have to have E9 times the whole half of the Virasoro group in between quotes. So all the group generated by all the negative modes of the Virasoro algebra. So I will also not explain this more, but what it also allows you to do is to define all your fields in the theory that will come afterwards into a higher, as transforming in a lowest weight, highest rate representation of this infinite dimensional symmetry group. So this is the direction we're going to take. So before showing you what's the shape of this twisted self-duality equation, which encodes all of these formulas, let me say just a few words about the algebra of these groups, because there was a question already on it. So there is, first of all, I mean, let me just remind you what's a loop algebra. So the loop algebra over E8 is just the space of maps from the circle to the algebra of E8. So it means that any element of this loop algebra can be expanded on the basis of on the Fourier basis, and that you can identify the generators of the loop algebra as essentially the E8 generator multiplied by the Fourier mode number. And so you have an infinite number of them. And so the loop algebra over E8 is just an infinite stack of copies of the E8 algebra, where each layer is labeled by the Fourier mode number. The affine extension is just the loop algebra over E8, which has the following commutation relation, and which is centrally extended by the following term. So there is a central charge, and the coefficient which appears in front, you were asking before. I mean, this is essentially what comes out from the central charge.
Franz, the X and A is just the coefficient of in front of.
Yeah, it's just a coefficient. Yeah, exactly.
The A should be capital, I guess.
The what?
The A.
The A is capital. You're right. Yeah. Yes. Yeah. So the affine extension of E8 is the loop. Group of E8 centrally extended by a central charge. So as I said before, we're also going to need the Virasoro extension of this whole setup. So you can introduce via this Sugawara construction a whole set of Virasoro generators which do not commute with the loop generators and satisfy the following relation. And I'll denote the full set of generators. So all the Virasoro generators, the loop algebra generators, the central charge, I'll denote them by T alpha. So alpha will be my adjoint index for the rest of the talk. And in fact, E9 is just the affine extension of E8 with the L0 generator, which acts as a derivation operator for the affine group. But that's not going to be so important. In the following, I will always get the full extension with Virasoro.
Central charge is just going to be one number, no? When it actually acts on the.
Sorry.
On the when you actually have the representation, so you're acting this E9 on your space, on your coset space, then the central charge is going to be a number, no? Like 1 or 2, or I mean, there's just
I'm sorry,
one
no,
answer,
right?
So
I mean, this is going to be 1. Sorry, that's what you were asking.
1?
Okay,
yeah, just a number. 1. Oh, okay, great.
Yeah.
Thank you.
Sorry, I got confused with the terms that were in front here. Yeah.
Okay, thanks.
So in order to continue and recast the dynamics and so on, I also need to introduce these shift operators. I call them SN. They will play an important role in the next slides. So essentially, I mean, what they do is in the name, so they just shift the mode number of the Lie algebra, or they also shift the Virasoro, the mode number of the Virasoro generator. And an important fact is that they annihilate the central charge. So this means, in particular, and this will play a role, that they are not an automorphism of this whole affine algebra, because essentially if you take the commutator of a generator which is shifted with another generator, it's not the shift of the commutator. Instead, it differs by a term which is proportional to the central charge. So this is something that is good to keep in mind. And the last thing I'm going to need is one representation of this whole E9 plus Vira0. I'll call it the basic representation. It's a lowest rate representation, which is built as usual out of an E8 invariant vacuum. The details don't matter too much. I will denote objects transforming in this basic representation by ket vectors, and in the dual of the basic representation will be a bra. Sometimes I'll use this ket, sometimes I'll use index notation, where here the EM is the basis. So I will kind of oscillate between the two notations. And finally, in this basic representation, I can define an involution or Hermitian conjugation, which acts as a dagger here, which just flips the mode number of the loop algebra generator or the Vira0 generator and leave the central charge invariant. Okay, this is all definitions that I had to give to be precise. But now let's move on to the dynamics. And as I said, to the twisted self-duality equation, which encodes this infinite number of duality relations. So it's based on the coset which I presented before. So here it's not quite E9, it's here at 8, but essentially the same. That's the affine group. That's the group generated by the negative Vira0 generators, and that's that's the maximal unitary compact group of 9. And it's defined as the subgroup whose elements satisfy the following property, where this dagger here is the involution I introduced before. Anyway, you have an infinite dimensional coset space, you have an infinite number of scalar fields that parameterize your coset space, and now the claim is that the whole dynamics is essentially encoded in the following equation. So here the star is just the hot star in 2 dimensions with respect to the flat metric, conformal gauge. And the S1 is the shift operators I introduced before, and this P here, so the form notation, so it's a P mu, it's a 1 form. And these are essentially the Morer-Cartan current that you can construct out of the coset representative for this infinite dimensional coset space. So the claim is that the whole set of duality relations is reproduced by this twisted self-duality equation, and you can actually check it for the first few levels. In order to do that, you have to pick a specific gauge, you have to pick a specific coset representative for infinite dimensional coset. And you can go to a Borel gauge. And again, here the details are not important, but you can actually spell out, if you want, a representative for your coset space, where you have an affine group element, which is parameterized by the infinite number of dual potentials. And you have an element for Vir minus, which is parameterized by the dilaton, and by an infinite number of extra scalar fields, which I call Vira0 scalar fields. As I said, I had to enlarge the group structure in order to use this twisted self-duality equation. If you plug this coset representative inside of the twisted self-duality equation, and then you look at the components of this equation along the Vira0 or along the loop. Along the Vira0, what you'll find is a set of equations relating all these Vira0 scalars, and you'll be able to integrate all these equations such that they are all expressed in terms of rho or rho tilde in the end algebraically. So the only fields you have left are rho and rho tilde, and it's the only duality, really true duality equations that's left. And if you plug this into what you get for the loop components of this twisted self-duality, you find all the nonlinear duality relations that I've presented before between the fields Y. So in this way, you recover all the duality relations whose integrability condition boil down to the field equations of the series. So it's quite convoluted, but in the end, it turns out to work. And there is a way to make this more formal, of course. So this is essentially the object we're going to work with. It encodes the dynamics of the theory, but you could have complained already because I said to you in the previous slide that these shift operators are actually not preserving covariance, are not automorphism of this algebra. So it means that this equation is not covariant. If you do an E9 transformation on this equation, or P transforms on the K of E9, so E9 or K of E9 kind of the same if you fix the gauge or not, then you'll see that this equation is not mapped into itself, but it differs by a term which is proportional to the central charge. So the currents are covariant, meaning that they transform as a commutator on the Kelvin transformation. So what you have to do is that you actually have to introduce a modified version of the shifted current with a term proportional to the central charge and whose component is a new field, which I call chi mu. It's not a new on-shell degree of freedom. It's just here to compensate for the lack of covariance of the first term, which is the shift of the Mohr-Cartan current. So this means in particular that chi mu transforms into P, and that P and chi mu form an indecomposable representation under E9 or K of E9, and that they transform as follows, essentially. But of course, so this is a field that will appear in the Lagrangians. We're going to write and everything, but on shell, it is just set to be equal to the Hodge dual of the central charge component of the current. So you're not adding any new degrees of freedom. It's just essentially a trick that will be useful to write down the theory in terms of covariant objects. Okay. So this is your final duality equation. I'll move on. And now you can ask, okay, can I write a Lagrangian for this ungauged model, which is manifestly invariant under this large symmetric group, which is E9 times V minus. And of course, the first thing that will need to happen is that it will need to involve all these dual fields that you have introduced on shell, because they transform under each other, into each other under this infinite dimensional symmetry. And you might also ask, okay, what's the point of writing a Lagrangian, or rather a pseudo-Lagrangian here? Because anyway, I mean, if it's a pseudo-Lagrangian, it means that when you take a variation with respect to the fields that appear in the pseudo-Lagrangian, you won't recover all the equations of motion of the series. So it means that you have to supplement it with the twisted self-duality equation. But you might object and you might say, okay, since the twisted self-duality equation already contains all the dynamics of the theory, whatever you're going to write is going to be totally redundant with the thing that you have to add on top of it. But the reason why we want to write down such a pseudo-Lagrangian is that when you will want to move to gauge supergravity and study covariant gauge and to study gauge deformations of the whole setup, this pseudo-Lagrangian will be a natural object to actually deform. So in the rest of the slide, I'll explain you essentially what it looks like, this pseudo-Lagrangian. So you might ask, okay, what could there be? There could be a kinetic term, there could be a topological term. So if you try to write the natural or naive guess for a kinetic term, what you would write is just the Mohr-Cartan current for this infinite dimensional coset space contracted with some invariant bilinear form. But actually, it turns out that there doesn't exist any invariant bilinear form over this affine extension of E8 plus V Razor. And the solution is pretty simple, and it means that there is just no kinetic term in the pseudo-Lagrangian. So it will just consist of a topological term. And then you might ask, okay, how do you build something which is manifestly invariant under A at 8 times V, and which is a top form in 2 dimensions? Then you think a little bit and you think, okay, maybe let me just start with the only top form that I know, which is equation which is covariant, and which is actually the Mohr-Cartan equation. So it's the K of E9 covariant derivative of P, which is equal to 0. So you have this equation, this is true. So here, again, I use a form notation. What's in bracket is the K of E9 covariant derivative. And then for a moment, you forget that it's actually equal to 0. And you say, what happens if I shift this equation, the left-hand side? Well, if I shift it, it's not covariant anymore, because the shift don't preserve the covariance. It's only covariant modulo a term proportional to the central charge. So if you want to complete this object to something which is covariant, you have to add something proportional to the central charge. And you have to add the K of E9 covariant derivative of this auxiliary field chi mu that I've introduced before as a component of the central charge term. So what do you have now? You have something that transforms covariantly on the K of E9 or on the E9. So it means that it transforms as a commutator. But the first term is 0 by the original equation. the whole thing transforms as a commutator, but the only thing left is proportional to the central charge. So it means actually invariant. So you have constructed an invariant top form in 2 dimensions, and this is actually the topological term you're looking for. So with this rather naive trick, you actually construct the right topological term quite quickly. So if you spell out what is this Yerevan covariant derivative of the field chi mu, if I open it up a little bit, of course, you'll get the partial derivative. And then you'll get a term which depends on the loop components of the of the Moer-Cartan current. So this is essentially a Vézimir term plus a bunch of other stuff that I won't describe. But it takes a rather nice form. What you can do is you can ask, okay, can I move from this pseudo-Lagrangian to true Lagrangian? And indeed, what you can do is you can take just pseudo-Lagrangian, you can make very non-trivial rearrangement of the terms, and you can write it out as a physical Lagrangian, which just depends on the 128 physical scalar fields that I've shown you in the beginning. So it only boils down to this Lagrangian, that's the physical Lagrangian, plus terms which are proportional to the twisted self-duality equation. So this is the way to actually extract back the physical Lagrangian. Okay, so now I've described the whole way to encode the dynamics of the ungauged supergravity in 2 dimensions. And the question I want to ask is how to turn on gaugings. Wow, yeah. Any question?
So can you understand this topological term in terms of the topology of this coset space? I mean, inside of the E9, you have some second cohomologies. There's like a 2-sphere, but then with a circle fibered over it with, set with a, Chern class 1, which is the central charge. So can you see it as somehow the embedding of your 2-dimensional space onto this kind of 3-sphere with some non-compact directions?
The 3-sphere, what do you see? Sorry.
So there's a 3-sphere in the sense that if you look at E9, there's the base space without the central extension, which has a 2-sphere, which just comes from the 3-sphere up in E8. It has a 3-sphere because of Cartan's theorem that every group has a 3-sphere. But you go to a loop space and everything goes down by 1, so it's a 2-sphere. Okay. Then the reason it has a central extension is because you've got line bundles over any 2-sphere, which are just given by their hop, the hop bundle. And you chose the one which has Chern class 1. That's why you have central charge 1. So you have a circle fibered over the 2-sphere. So I'm wondering if it's like if you could have a West-Amino term, like, interpretation of this topological term that you found.
Yeah, I don't know what to say. It's a good question, but it's no, I have no idea, to be honest. No? I have to think about it.
Okay.
Yeah.
But it's not a integer, is it, right? The topological term?
No, it's not.
No, good.
No.
Which it shouldn't be.
And there is this field, there is the dilaton row in front also.
Yeah. Okay.
Yeah.
So, is there any other thing you can say characterizing it as far as try to understand what this makes sense of it?
I would have, once you know what it is, you would have said, okay, what else could it be? Because if you're supposed to write down a pseudo-Lagrangian, and it has to be somehow manifestly covariant, it could only be the external product of a covariant derivative with a 1 form, and it's the only thing that you could write in the end, in the theory. But yeah, of course, once you know the answer, it becomes obvious. But took a little while to realize. But I can't say more. Yeah. And indeed, if you take also, let me say that if you take variations with respect to different fields here, you reproduce parts of this twisted self-duality equation, but not all of it, which is the reason why you have to impose it on top to have the full dynamics.
Right.
But also this whole trick that I use to come up to this topological term, it's also quite useful because it's just naturally deformed by the gauge transformation that I will introduce right now. So like the extra effort you have to make to go to the gauge case are really minimal. So that's also something that I want to be clear. So if you turn on gaugings, what you're going to do is you're going to select a subgroup of this potentially infinite dimensional subgroup of this rigid symmetry group, which is the affine extension of V8 times negative part of VR0. And to move to the gauge theory, well, you know already that there will now be a scalar potential for the scalar fields V here. And that's what you are afterwards in a generalization of the topological term. So what you do is you introduce gauge fields as minimal coupling. So your derivative are promoted to now covariant derivative with covariant gauge, with gauge fields. And you use, at least here, I use what's called an embedding tensor, which I called theta m alpha. So it has an index in the dual basic representation and an index in the adjoint of this big algebra. And it essentially tells you which subgroup you will select to gauge. So it will be a subgroup of this hat E8 times minus. And as I said before, you cannot select any subgroup. I mean, there are certain constraints. And for this reason, an acceptable embedding tensor must satisfy a certain algebraic condition, which ensure that the gauge algebra will close, and certain representation constraints as well. So it means that it's not just in the tensor product of this dual basic representation in the adjoint, it's actually projected on some sub-representation to have a consistent gauging. But I will not go more into this. So now with your covariant derivative, you reconsider your currents, P mu, and you covariantize them just by using your covariant derivatives. And you say, okay, what is the topological term going to look like? So you use the exact same trick. So now you don't have the Moer-Cartan equation, which is Yerevan covariant derivative of P equal to 0. Now, because the partial derivative is promoted to a covariant derivative on the gauge transformation, it's not equal to 0 anymore. It's equal to a term which is proportional to the field strength of these vector fields and to the embedding tensor, which specifies the gauge group. And you can play the exact same trick. You can say, okay, I shift this whole thing, I covariantize it, and I know that the K component will give me my invariant topological term. So it looks just as before, except that now we have always covariant objects. So this is the KOV9 covariant derivative in terms of gauge covariant current. It's a bit convoluted. And then there will be some extra term which look, which I definitely don't want to write, which depend on the field strength for these non-abelian vector fields. And so I just write it schematically as this ball D for KOV9 covariant. And this is the extra fields which depend on the field strength, depend linearly on the field strength, linearly on the embedding tensor, as well as on the scalar fields. So this is your result for the topological term. And now you ask, okay, but what is the scalar potential of the theory? And this is where things will go wrong. Because normally what's happening is that when you start introducing gauge couplings, if you would have started with supersymmetric transformation, you would have had to deform supersymmetric transformation by these gauge couplings. And so this would have created certain Yukawa couplings, and then you would have had to compensate for this presence of Yukawa couplings by scalar potential. So the scalar potential in the end is basically fixed by supersymmetry. But as I said before, in fact, making supersymmetry work in the presence of these gauge couplings is a long-standing problem in D equal to 2. And so there is no way to actually get access to it without, without getting it from Kaluza-Klein truncations. So that's the second part of the talk, but in view of the time, I think I will skip this part. I don't know, are there any questions? No? Okay. So what I can say just about, the issue is really about writing down these Yukawa couplings. And for this, couplings between scalar fields and fermions. The scalar fields in the theory transforms under this numerator, on the hat E8 times 0 minus, and the fermions turn out to transform under this KOV9. And we don't know how the basic representation, essentially, in which the bosonic field transform branches into representation of this KOV9. So you're missing actually the Clebsch-Gordon coefficient to be able to write down this Yukawa coupling. This is a problem at the level of the mathematics. That's the reason why you're stuck if you want to derive the scalar potential by SUSY. And one last thing I want to say is now also that we have introduced gauge couplings. The pseudo-Lagrangian is not redundant anymore with the twisted self-duality equation. I mean, you will reproduce part of the twisted self-duality equation, but if you vary with respect to the vector fields, for instance, this is definitely not contained in the twisted self-duality equation. So the full dynamics is really the two. Okay, so I will be very, very quick on the Kaluza-Klein truncation. So as I said before, instead of starting from just even dimensional supergravity or type 2b supergravity or so on, we use a reformulation of these higher dimensional supergravities, which makes the whole duality symmetries of two-dimensional supergravity manifest. So of course, what I'm going to describe now very, very quickly is not going to look at all like higher dimensional supergravity. And that's precisely the point. It's going to look exactly like what I already presented you before in 2 dimensions. And because it looks so similar, it will be very simple to actually perform a Kaluza-Klein truncation. So let's go through it quite quickly. I mean, there are many, many details, and it took us quite a lot of time to build this reformulation, but I will really skip as much details as possible, focus on what's important. So in particular, the fields of this reformulation, they look exactly like the ones I had in 2 dimensions before. So you have some scalar field, you have this auxiliary time mu, you have these vector fields. Now, the difference is now they all depend on a full set of external coordinate and internal coordinates. So 2-dimensional external space-time and internal space parameterized by the coordinate ym, which a priori, you have an infinite number of them. They transform in the basic representation. And so the whole theory essentially reproduces higher dimensional supergravity in a certain Kaluza-Klein split. So accordingly, you have partial derivative in the 2-dimensional external space and internal derivative internal space, which are called dm, or sometimes are written as brush. Now, the difference with the 2-dimensional gauge supergravity is that here your whole reformulation of the higher dimensional theory, it doesn't need supersymmetry to be completely fixed. You can fully fix the bosonic dynamics by one single type of gauge symmetry, which are known as generalized diffeomorphisms, which are generated by parameters which also depend on the full set of coordinates, and by a generalized derivative, which takes the following form. The details are not important, but this is a very powerful gauge symmetries of your reformulation. It looks very much like the standard Lie derivative for gravity, in the sense that it has a transport term and a rotation term, but here the rotation terms, they don't have a GLN structure as for gravity, but instead they have this E9 structure and this Wehrlein structure. And the point is that if you impose on your reformulation this gauge symmetry, you fix the whole thing. So yeah, I rewrote it just in terms of Braz and Ket. And there is one more thing that I need to say, which is important, which is that in order to have closure of this gauge symmetry generated by this generalized derivative, you need to impose a constraint on all your fields, which take the following form. So here, phi and phi prime are arbitrary fields or parameters in your reformulation. This is a covariant tensor. These are derivative with respect to the internal coordinates. And your reformulation only makes sense if you solve this constraint, which is a constraint on which internal coordinates the fields are actually allowed to depend on. So they cannot depend on an infinite number of coordinates. You have to pick a physical slice, you have to pick a physical subset of physical internal coordinates to solve this constraint. The solutions to these constraints are known. I mean, one of them is trivial in the sense that you say nothing depends on the internal coordinate y, in which case your whole reformulation boils down to ungaged supergravity in 2 dimensions. And if you want to keep internal coordinates, and as much as you can, there are 2 different inequivalent solutions to this constraint. One of them, you keep 9 coordinates and your whole reformulation reproduces 11-dimensional supergravity in a 2 + 9 Kaluza-Klein split. And the other solution, you keep only 8 internal coordinates, in which case you get 2e supergravity in a 2 + 8 Kaluza-Klein split. So depending on which solution to the section constraint you're choosing, which coordinates you decide to keep, you're actually describing different higher dimensional supergravities. Once you have done that, the generalized diffeomorphisms here, they encode the internal diffeomorphisms and the internal p-form gauge transformations of the theory. Okay, so now what does this reformulation look like? As I said, it doesn't look at all like high-dimensional supergravity. The whole dynamics is going to be casted in exactly the same form as in 2 dimensions. So you have a topological term, you have a potential, you have a twisted self-adjoint condition, and everything will be built in terms of 2 different kinds of current. You'll have external current and built out of your scalar fields, which now depend on the full set of coordinates x and y. So in terms of some covariant derivatives with vector fields and so on, these currents will be completely covariant on the generalized diffeomorphisms, which is now the gauge structure that deforms the theory. It's the analog of the gauge transformations in 2 dimensions. And so this external current, they will enter the expression of the topological term. You can play the exact same trick as I played before to construct it. But now you also have internal current, which are built using internal derivative of these scalar fields. I call them PM, with the index M coming from the internal derivative, or you can also write it as a bra, because it transforms in the dual of the basic parameterization. And these are the currents which will essentially build up the scalar potential. The scalar potential here will be quadratic in this internal currents. And this scalar potential is what we're looking to actually reduce, do Kaluza-Klein truncation off, because this is what's going to give us the scalar potential of gauge supergravity in 2 dimensions. But here it's fixed entirely, the expression of the scalar potential, by the gauge symmetry, which are generalized diffeomorphisms. So I just flash the expression because it is what it is. Since the internal current are not covariant, you don't expect a nice expression, and indeed it's not nice. It looks as follows. So it depends on the scalars, it depends on the internal current. It's quadratic in the internal currents, you have several terms, and the point is that now everything depends on the full set of coordinates. Everything is invariant on the generalized diffeomorphisms. You have your exceptional field theory scalar potential, and you can check, which is what we did and which is very non-trivial, that when you choose now a subset of coordinates to be physical, so the fields only depend on 8 or 9 coordinates, then this whole dynamics reduces to 11-dimensional supergravity or type 2b supergravity. This is really a non-trivial check, but this is the way to do it. So now you have a reformulation of these higher-dimensional supergravities, which look very, very similar to the gauge supergravity in 2 dimensions that you're looking for. So this setup is actually really convenient to study now Kaluza-Klein truncations to 2 dimensions. So that this will be my last slides. I have two or three slides, and just say a few words on what the truncation ansatz look like. So the idea is that you're going to consider essentially a very, very simple truncation ansatz. It's called the generalized Schwarz truncation, where you're going to express all the fields of the exceptional field theory, which depend on x and y coordinates, so the scalars, the vectors, also the gauge parameters. You're going to express them in terms of the fields which depend only on x, which will be the fields of the gauge supergravity that you're looking for. So you have the scalars again. So here I differentiate them by putting curly and straight. So the scalar fields V, the vector fields, the gauge parameter, the gauge transformation, and gauge supergravity. And the ansatz is given in terms of what's called the twist matrix, which encodes all the dependence in the y coordinate. And this twist matrix is an element of the large duality symmetry. So the affine extension V8 and V minus. Importantly, it depends only on a physical set coordinate. So it respects the section constraint. So now if you assume that you have found a twist matrix, an actual one that you construct in matrix, you can describe explicitly, such that a generalized diffeomorphisms in exceptional field theory on any field of your theory reduces to a gauge transformation in gauge supergravity in terms of an embedding tensor which specifies the gauge group and an embedding tensor which is constant. So this is a very strong requirement to be able to find a U such that the embedding tensor is constant that you obtain gauge supergravity. Then you have defined a consistent truncation, because if you plug this ansatz into the dynamics of XFT, the Lagrangian just, the whole Y dependence factorizes out of the Lagrangian completely and leaves the gauge supergravity Lagrangian that you were looking for. So that's, of course, I mean, because the ansatz are simple, it's something that is not too hard to prove, but I won't go through the steps here. And the same is true for the twisted self-gravity constraint. It just reduces immediately to one gauge supergravity. So here, this U of y L0 is the L0 component of this affine element U of y. So by doing this, since you know the expression of the scalar potential in exception field theory, by plugging this ansatz, assuming the twist matrix satisfies this, you can actually read off the expression of the scalar potential in gauge supergravity. And this was the reason why we did this whole loop through higher dimensions to get to here. So first of all, let me tell you what we get for the topological term. Well, you get exactly what I had constructed straight in 2 dimensions. So Yerevan covariant derivative of chi, and then term proportional to the field strengths and so on, an embedding tensor. And you get, lo and behold, the scalar potential for gauge supergravity. So now everything only depends on x during 2 dimensions. So what appears in fact, it's quite remarkable that the expression is so simple in the end. So it's expressed in terms of the supergravity scalar fields, V, which depend only on x and which I've packaged into this Hermitian matrix. It depends on an invariant bilinear form, which I call eta minus 2. So I told you there is no invariant bilinear form over the full hat E8 plus V, but you can define one over height E8 plus LK, one of the Virasoro generators. So that's the one for N minus 2. And in terms of the embedding tensor, or at least the projection thereof, so this was the embedding tensor I introduced before, and you can express it in terms of this component here, which characterizes the gauge group. So I insist here, all the fields only depend on 2 coordinates, and you can check that all of this is fully gauge invariant under the gauge transformation of gauge supergravity. So what we have constructed, what we've obtained here, is the full dynamics of all d equal to gauge maximal supergravities that results from 11-dimensional consistent truncation of 11 or 10-dimensional supergravities. So it's important I say that because it doesn't mean this captures the most general dynamics of any gauge supergravity in 2 dimensions. I mean, it's only a subset that arises from consistent truncation because by definition, we build it like this. Okay, to conclude, let me just tell you the last thing we did without going into details. We actually worked out a specific example. And what that means is that we actually constructed a twist matrix U such that this condition is satisfied and such that the embedding tensor here of the gauge supergravity you obtain by doing the consistent truncation induces an SO9 gauging of the theory in 2 dimensions. So, I mean, of course, the gauge group has to be a subgroup of E9. And here it's worth mentioning that you have to be careful what you can gauge and what you cannot. So in particular, the twist matrix that produces this SO9 gauging, the SO9 is part of an SL9, which is in E9, but there are different SO9 which are part of different SL9, which are also in E9 and also in E8. And these ones cannot be gauged, but this one can be gauged. So in particular, the gauging we do is not part of the E8 group of gauge supergravity in 3 dimensions. So by constructing this twist matrix, we actually proved the consistent truncation of 2A supergravity. So in our twist matrix, you have only 8 coordinates, which are the 8 coordinates of type 2A. So it proves the consistent truncation of 2A supergravity on the 8th sphere. It actually corresponds to the 8th sphere, to a 2-dimensional supergravity, which is maximal and has an SO9 gauging. I won't present the Lagrangian, but it can just be worked out from the general form that I've written here. And it's an interesting theory. As I said in the beginning, I mean, it has a very rich structure of vacua a priori. There is an immediate solution in 2 dimensions that you can write down. Is the solution where you put most of the scalar field, the coset scalar fields to be constant, the gauge fields to be 0, and you have a non-constant rho, and you have essentially a domain wall. So the metric of the domain wall with non-constant rho. So this is a solution which preserves the SO9 invariance of the gauge supergravity and corresponds to a half supersymmetric domain wall. It's not maximally supersymmetric. And you can use or truncation ansatz to uplift the solution, you can check that it indeed corresponds to the D0 brane, the near horizon geometry of D0 brane, whose geometry is a warped ADS2 cross S8 with certain fluxes. So the reason why you have warping here is because you don't quite have ADS2 in 2 dimension. You have you have this dilaton, which essentially breaks the conformal symmetry of the solution, the SL2 symmetry. And what's interesting now is that you have the knowledge of all the fluctuations around this warped ADS2 cross S8 geometry. And you know that if you study these fluctuations in supergravity, you should be able to compare them with the dual theory, which is the supersymmetric SUN matrix quantum mechanics, and which is known as the supermembrane model, or also sometimes the BFSS model. And so this is something that we're looking forward to actually explore with this holographic duality, because now the whole supergravity setup is in place. Okay, I might have, yeah, I went over time. Sorry about this. Thank you. And, yeah.
Sorry, I was muted. So thank you, Franz. We can start with questions.
So this SL9 hat is affine SL9 and the previous.
Exactly. So that's the affinization of the SL9, and both SL9 here are contained in the affinization of SL9, but this SL9 here is not part of E8.
So what's the embedding for the affinization of SL9 inside of E9? I mean, it's not, you're using something which is at non-zero in the loop group, right? Otherwise you wouldn't be able to get an SL9 hat maybe inside of E9.
So in particular, E8 is not in the SL9 type.
Right, right. But also you're not just using the, I mean, how are you constructing the SL9 hat? Like what are the Cartan generators in terms of the E9 Cartans?
So this SL9 hat is constructed, it's the loop extension over the SL9 that contains the SL9 that is gauge here.
All right, but I'm wondering about the last inclusion. I mean, the one on the right.
The other SL9 here includes, I mean, they have a common SL8.
Right.
And this SL9 have a common SL8, but the way it's completed to SL9 here is by using generators, which is out, yeah, which is at different level in SL9 hat. There's a spectral flow between the two SL9.
Right, that's what I'm thinking. So this last inclusion on the top line, in order to make the SL9, I mean, just in order to make the SL9. So if you're embedding the SL9 in the E9, you're using something which isn't at level 0 in the loop group, right? You're using something which has some winding in the loop group, right?
Yeah, this is yeah.
So there's an SL8 in it, which is all at level 0 in the loop group, and then just to go up to number 9 is just one of the Cartans, which is somehow outside one of the Cartan generators, or how are you doing it? And there's this usual construction of SL2 times SL2 inside of Virasoro, so maybe it's some trick kind of like that.
No, so it's not. It doesn't have to do with the Virasoro, but it's more that you can. So they correspond to different spectral flow essentially. So it has to do with the breaking on the E8. So if you take this SL9, which is in E8, and you break it into SL8, you have how does it work again? I have to check. You have the adjoint of the SL8,
okay.
And then you have it's completed by the 8 of SL8 and the 20 something of SL8 to SL9. Okay, of the 8. Now you affinize the whole thing, and this other SL9, and the affinization is the same as this one. I mean, there's only one. It's just like kind of tilted.
Yeah, the affinization is the same. We're just learning about the SL9 itself.
And then the other SL9, it's you take the SL8, which was at level 0 of the affinization, but the completion to ESN9 is located at higher level in affinization or lower level. It's not you mixing the level.
Right. So, okay, so just when you're adding the very last Cartan generator, that one
I think so, yeah.
goes up. Okay. Okay, thanks. I try to understand where the S8's really living here, but that's okay. That gives me some idea.
So thank you, Franz, for the very interesting talk. So I missed the beginning. So could you remind us the definition of vacuum that you're using of the theory?
Well, actually, it's a good question because depending on who you ask, people have different opinion. But so here I really just mean a solution of the field equation. This is maybe just to give a flavor. I guess it's not like I need to hit you harder with anything, but I mean, this is the complexity of the scalar potential of this theory is quite remarkable. I mean, it's there's a lot to explore. It's the only known solution essentially so far. And so I'm curious, for instance, whether there could be other solutions. For instance, not preserving SO9, but maybe something like SO3 cross SO6 that we could immediately uplift because we now have the truncation ansatz, and that would correspond to another type of matrix quantum mechanics, like BMN, for instance. So that's something I'd like to see. And there's also another thing, which is that I would like to clarify a bit. I mean, there's a lot of work with having two-dimensional gauge supergravities or gravity as an effective description of the dynamics around the near horizon geometry of external black holes. And people somehow seem to perform the truncation to two-dimensional theory in a very rough way by throwing a lot of modes, and it's not always for me completely clear that what they're doing is very rigorous.
That is four-dimensional black holes. Right?
Exactly, yeah. Four-dimensional extremal black holes. I mean, any extremal black holes has an ADS2 near horizon factor, but people are doing it mostly for four-dimensional black holes. And so they do a truncation to two-dimension to dilaton gravity in two-dimension, and with the truncation, yeah, to me, it's not always clear that it's really consistent what they're throwing away in terms of mode. And in particular, I'd like to see what's the relation with the gauge supergravities we obtain here, because yeah, I mean, there should be one. In particular, how is this? In a way, JT gravity should be a point in this, but yeah.
So it's not clear from this construction coming from like 10D or 11D supergravity how you see JT as part of it.
No, I mean, it's not, because I mean, it's a really strong truncation if it is there. You would have to truncate a lot more fields.
A lot of stuff.
Exactly, yeah. And I mean, then there's JT, but sometimes people keep a bit more, like additional scalars or some gauge fields. But in a way, I mean, it should be in there. But maybe because this is in a way too complete, it's difficult to see.
Yeah,
hopefully it's in there.
One more thing I wanted to ask was that, like, is there any known example where one does some truncation and then in the low dimensional theory you have some weird situation like having more than one gravitons?
Well, what do you mean by more than one graviton? Because I mean the graviton, when you compactify, you have to expand on some basis of eigenmodes, or you have massive modes and massless modes for the graviton.
No, I meant like having more than one massless. So is there any possible way to get that? Like, I mean, you have this extra coordinates dependence. Naively, standard Kaluza-Klein would say that apart from the zero mode, everything is massive. But there might be some different truncation where you have more than one massless. I'm just curious.
Well, what if you compactified onto the product of a manifold with itself? Then you'd have one graviton on each manifold. So maybe that's kind of like what you're looking for. If the off-diagonal parts were massive.
Okay, so you would have two, or you would have more?
Well, I mean, you'd have more, but maybe things become massive depending on the product part of the metric. But I mean, you know, you have other fields around. But anyway, you'd have two. If you just compactify onto m times m, then you'll have a graviton on m and a graviton on m, no? I mean, you'll have a metric on m and a metric on m.
This would be internal metric. I mean, I think he means graviton for the external space.
Well, I'm saying if the external space it was a product, then maybe you would see.
So you're saying that you identify one of the internal space becomes also identical to the external space?
Well, no. I mean, if you had an internal space which was a product of something with itself, and it's a kind of stupid way to do it, but just, you know, if you wanted to prove you could have two gravitons.
Yeah, but for that you don't have to compactify.
Well, you don't have to compactify, but if you don't do any compactification, then you're going to have all the off-diagonal parts too. So you just have the whole thing. So you want some way to try to make the off-diagonal parts massive. So compactifying gives you some space to play in.
So this somehow reminds me the situation when if you put together a stack of brains, then you get the non-abelian cage theory or something. Is it somehow analogous, or it's just a false analogy?
No, I don't know any analogy there. I mean, there it's just because you get a stack of brains, you have the strings which go from one brain to another brain, and they fill in the W bosons. But I don't know anything like that with gravity.
Well, yeah.
I mean, not to the stupid trick I was suggesting. Maybe there's some more clever way to make two gravitons, which is similar, but.
Yeah. I mean, naively would be interesting to see if there's a way to have some sort of non-abelian algebra of gravitons that would be part. At least in 2 and 3 dimensions, we know that there is scalar gravity. Whether this can be embedded into this higher dimension.
Whether this can be obtained as a compactification. But it's I mean, it's not on a fixed background. It's really just arbitrary background. It's a question I'm asking.
Yeah, I mean, we know at least fixed background ones. Well, in a sense that not that it's arbitrary background, but I mean, the examples we know are we know also what kind of backgrounds that they admit. Like it's like gravity with cosmological constant. If you want maximally symmetric background, you given cosmological constant, it's uniquely known. In the same way, if you want to have like ADS as a maximally symmetric background for your colored gravity, then it's basically uniquely fixed possible theorem. I mean, there is always a single graviton that is the one that couples to everything universally, and then the rest are some other massless spin-2 modes that
Yeah, no, I mean, I definitely don't know of any example, but
I wonder whether these are really hard to get, or it's just whenever people see something like this, they throw away as unphysical. Sometimes it's a self-fulfilling prophecy, right? You don't want to get it because you think it's weird, and then somehow you also say that this is not possible because nobody does it.
Yeah.
Anyway. So one more question I had was related to this. So you wanted to write the Lagrangian that would give you this twisted self-duality equations, and then you stumble on this problem that there's no invariant bilinear form, right?
Yeah.
So this I mean, at some point I knew details. We noticed some time ago that actually Virasoro algebra does not have a invariant bilinear form. So I'm wondering if this problem is stemming from Virasoro, or affine E8 itself also doesn't have a invariant.
So no, it's not Virasoro. It's not affine E8. It's the mixing between the two forms.
But separately, if you take affine E8, do you have an invariant bilinear form?
Yeah, yeah, for sure. Yeah, exactly. So that, which is, I mean, this invariant bilinear form, there is one on affine E8. And if you take k is equal 0, so which is affine E8 plus L0, this is E9. So that you have one for nk. But for instance, if you try to do, if you take, let's say, the SL2 subgroup of Virasoro, so generated by L-1, L0, L1, and you try to find an invariant bilinear form over affine E8 plus SL2, there it doesn't work either. You really can only pair a single Virasoro generator.
I see.
Yeah. Yeah. And yeah. That's so. I mean, of course, it's not really proof, but at least that's the reason why we don't get a kinetic term. You take this topological term and you do this reshuffling of fields in a way that you really break manifest duality symmetry, where you write it as splitting the physical action, which only depends on rho, sigma, and its scalars. Then this one has a kinetic term.
So when you refer to topological action, this term, I mean, if you have only this term, just topological part, then it would not describe any propagating degrees of freedom, right?
Well, I mean, it's not. No, I mean, I think it still describes some of the dynamics of the scalar fields. You have rho in front of this derivative, and I mean, it reproduces part of the twisted self-duality, which itself contains actual dynamics. I mean, it's so in a very, I mean, it's very non-trivial, but it must somehow include some dynamics.
But why do you call it topological? It doesn't depend on metric. That's the statement.
Yeah, exactly. It doesn't. I mean, you could even say, okay, you're in conformal gauge. So what's the metric here? But it doesn't. I mean, it has the typical shape of a topological term. It's compared to the one where you actually contract the two currents by, in this case, Minkowski. This is the distinction I made between the two.
So if it doesn't depend on metric, how can you have a twisted self-duality equation in it?
If it doesn't depend on metric?
Yeah, the twisted self-duality equation uses metric, right? So
no, it's well. Yeah, I mean, okay, here it doesn't, because again, I fixed, this is just the, with respect to the flat metric, but still, you're right. But it's more that you see here, it tells you that the component of P, let's say at level 0 in the loop algebra, its Hodge dual is related to the level 1 component. But so if you apply Hodge duality several times, you will get that, for instance, the level 0 P is related to the level 2 P. You get a cascade of duality equation by just applying Hodge duality all the time. And this is what appears in the topological term when I say twisted self-duality here. You get P0 minus P2 or Pn plus 1 minus Pn minus 1 with n sum that.
Oh, I see. So that when you add 2 times, then
Exactly. I mean, here I simplify things, but you in fact have a whole cascade. And I mean, I simplify many things, but here this means that you have an infinite number of shifts of P, and you have an infinite number of chi mu. But yeah.
Oh, I see what you're saying. So,
Yeah.
This is probably possible only if you have infinitely many of this piece, right?
Of what?
Infinitely many of this dual scalars. So
Yeah, exactly. I mean, otherwise you will over-constrain the system. You will have too many equations, I think.
yeah.
In a way, I mean, again, this thing here is. When you see it, you think, okay, what else could it be? But you know, like some very smart guy suggested it out of the blue, and months later we realize it's the right thing. But in a way, I mean, if you want to just relate all these dual fields that appear at different levels, and you want to write an equation which is covariant under the symmetries, there's not much more you can write. Yeah.
So can you go to the covariant equations just for the?
Sorry?
At some point you showed the covariant way of writing the equations, at least the E8 or E9 covariant, like all equations with all the scalars, right?
Yes. No, so you mean the full invariance under the affine and so on? Yeah, it's here. So that's the way to write it, where P1 defined as follows. But yeah. Yeah, and chi mu appears in the Lagrangian, as I said, but on shell, I mean, it's not. Yeah, but that's also the reason. You see, I mean, you might have asked, okay, my topological term is the Yerevan covariant derivative of chi. I've wrote chi1 here. I should have just wrote chi. But how come then, if I do Yerevan transformation on chi, I generate a Vesumino term where I see like the loop components of the currents appearing? It's because these strange properties of chi and p, which transform into each other under Yerevan as an indecomposable representation. That's why when you open up the covariant derivative, you actually generate terms dependent on p. Otherwise, I agree that it would have been very empty, the topology.
One last question, maybe. So the dimensional reduction you mentioned is very hard, so you need to write in some more convenient form the original theory to start with. So is there any kind of difference, what is the action that you use, or you are working with the equations of motion in the reduction?
So here we did it at the level of the action, but truly, I mean, what actually makes sense is the field equation. But you see here, if you do it at the level of the action, you find that the y dependent doesn't disappear, but just factorizes out, such that it would really be the same also in the field equation. But first of all, I should say that I mean, this is a trick to rewrite the higher dimensional theory to be able to write down simple ansatz formula like this. But back in the days, people did it just the hard way, like on S7. If you look at like the truncation ansatz, this is quite horrible, and we proved it the hard way. So it's possible. It's just much more difficult. Yeah, but I mean, since a few years, I mean, this type of reformulations known as exceptional field theory, I mean, they have really boosted the discovery of various truncations, consistent truncations. I mean, in this case, I'm really restricting myself to truncations from maximal supergravity to maximal supergravity. You also have the same technology to also do truncations which are consistent and break supersymmetry. So people have proven, found many other examples of this kind. Because you see, I mean, like in this reformulation, you really, on the left-hand side, you have completely taken your higher dimensional theory, you have done this Kaluza-Klein split, and you have really shuffled every degree of freedom in a very, very complicated way. In particular, like in the scalar fields here, you have pieces from the 11-dimensional metric, the one which have indices in the internal space. You have pieces of the p-forms in the internal space, where all the indices are in the internal space, and so on. In this vector here, you have also pieces of the metric, where it has only one leg in the external space. So you take everything, you completely reorganize, and by some magical way, you manage to make it look like exactly what you want to obtain after truncation, where the whole gauge structure of the theory, which is in higher dimension, it's diffeomorphisms and p-form gauge transformation, they somehow come together in this generalized diffeomorphism. And this is the gauge structure of the theory, which really resembles the gauge structure in lower dimension described by this embedding tensor formalism.
I'm just curious if some extra simplification could come by using some different forms of the action, and that would.
Well, I mean, it's not obvious to me how, because it really looks the two actions, the XFT and 2D, they look very much the same, except for the potential, of course, but that's the whole idea. But it's possible, I don't know, because you see, like, I mean, I put these dots everywhere, but I mean, they are, in this reformulation, in this exceptional field theory, there are additional fields which I didn't talk about, which don't have a counterpart in lower dimensions. So the ansatz are not so nice. I mean, there are fields here whose ansatz involve already the fields that you see here, the blue fields here. So, and these ones somehow have a kind of a special role to play, and this is not so nice. But you know, so I don't know. Maybe it could be that there is even a more general structure that you can make emerge in higher dimension. People have been looking, I think, for this also. I'm not very I don't know much about it, but I think all these algebroids and stuff like that. I think people are looking for this more general reformulation.
But just the naive one, for example, if you are in working with type 2b, then you have this self-dual field. Well, you can use the equations, of course, but you can use either the pseudo action or an action that would give you this self-dual equations. Would there be any difference at some level in your derivation?
Sorry, wait. You say you
Type 2b, you have either pseudo action or a real action.
yeah. And you say you mean whether my reformulation is based on a pseudo action or a real action?
Yeah, I mean whether there would be difference using real action or the pseudo action. I mean,
yeah, I mean, in the end, one thing I have to say is however you write it, you're still always doing supergravity. There is nothing more. So then it might boil down to the same.
But I mean, you can have it written in certain variables where you have actually more symmetries.
No, yeah, I agree. I mean, you could very well ask, you know, this XFT we've done here, which the dynamics look like this here. There might be another way indeed to write. I mean, actually, I'm almost certain that there should be another way to write with a real action instead of having the pseudo one. I mean, there would be a few options to tackle that. I mean, you could already ask this question in lower dimensions in 2D since the structure is the same. You know, like you could say, yeah. For instance, here, for the ungauge theory, so we went to a pseudo-Lagrangian, but most likely if you drop, like you know this very well, but you probably apply your approach to this. But you could also apply, you know, the Teitelbaum and so on, where you would break the 2D diffeomorphisms even more. And where you would be able to realize the full symmetry here with a real Lagrangian and without this twisted set duality. So I think
my question is whether actually it is possible that if you start from the system in the higher dimension where this is already realized in a certain way, the reduction would give you the real action, not the pseudo action. I mean, you could get it for free if you start from the right formulation. That's the idea.
So you mean you would start with the pseudo in higher and you would get the real?
I would start from the real action if I write action that gives me the right equations, and then do some reduction. I mean, I don't know. I'm just which would give me immediately a formulation that has the right action.
It must be possible, but I wouldn't know how to implement it immediately because I'm less familiar with this real Lagrangian in even dimensions, and so. But yeah, I mean, what you suggest must be possible.
So basically, in this two-dimensional one, you are this part I didn't completely understand. So you are imposing by hand the duality equation.
You have to, otherwise you're missing something.
Yeah. But and the lower part of this your slide, you write L top is physical action plus twisted self-duality squared. So what does it mean? Is it a way to actually get this twisted?
Yeah, it's a way to recover an action depending on a finite number of scalar fields.
Okay.
And the action that I presented in the Lagrangian that I presented in the very beginning. So this one.
I
This
see.
is what I call the physical Lagrangian, which only depends on the zero mode. If you're on the E8 scalars, there are 128 scalars parameterizing the sigma model here only.
Oh, I see, but it doesn't have the full symmetry. So
No, exactly. It doesn't have the symmetry. Only the sum of the two will be symmetric. But there is a way of rewriting it, which is quite non-trivial, where you can see this piece and the other piece.
Okay, I see. No.
And in fact, you can, I didn't mention this, but once you complete this thing here, for when you turn on the gaugings, you can do the same. You can write a real Lagrangian. You can write a real Lagrangian, which only involves a finite number of scalar fields for any gauging. Yeah, but you'll have to do what's called, you have to pick a frame, in the sense that
again, you lose.
You lose, of course. I mean, anyway, when you turn on a gauging, you break E9 and so on, because your gauging is so far. But with this embedding tensor formalism, you don't really see it, because how the embedding tensor transforms also. So that's the way to kind of describe it in universally covariant way. But as soon as you fix the embedding tensor, you pick the gauge group, then you have broken this duality symmetry. Nevertheless, you can do it. You have your pseudo Lagrangian, you fix your embedding tensor, and you can show, and you still have, presumably, you can show that you can rewrite the pseudo Lagrangian in terms of a gauge Lagrangian with a finite number of fields plus twisted self-weighted square. Yeah. In fact, I don't know if I have it. No, that's the potential for SO9. So for instance, it's not going to teach you much, but the SO9 theory, once you have fixed the embedding tensor, this is the potential. And if you actually look at it deeply and know what this symbol means, you will see that it really only depends on the conformal factor, the dilaton, and 128 scale. But but it's very non-trivial that it comes out from this form of the potential. But because you choose a specific embedding tensor, somehow you project out an infinite number of terms in this expression, and only a finite number of fields fixed. Yeah. So in a way, I mean, it's nice to have this. It's a very general expression, but when you want to actually look at a specific theory, you have to do a bit of work to get something you can look solutions of. Or I mean, I should also say that although this is all for maximal supergravity, in a way, this whole business of having some infinite dimensional group in 2 dimensions is quite independent of supersymmetry. I mean, this is all related to the fact that you're doing reductions of gravity to 2 dimensions. So if you take Einstein's theory in 4D and you put it on a torus, you will also get an affine group that's known for a long time. And the structure of the theory will be very, very similar to everything I've said. I mean, it's just that instead of having the affine extension of E8, you will have the affine extension of S8. But otherwise, everything will be the same. Everything will be the same. And in a way, also, the formulas, they don't really refer to the fact that you have E8 instead of SL2. But, so we wanted maximal SUSY because we wanted the origin in 11D, in the maximal supersymmetric theory, because we want a string theory interpretation of the whole business. But if you're just interested in GR.
Topological theories in 2D and 3D are basically well known. So the action, topological action you get, is it possible to somehow understand as like, I don't know, PF or something of that sort?
Yeah. Again, it's not a real action. I mean,
Yeah, I mean, even the pseudo
yeah,
action.
it's
That's still helpful to think in terms of some known topological theory and then some truncation of it by imposing an extra condition. But yeah, again, I think I made the loop. I came back to the question. So if it was a real topological theory, then it wouldn't have degrees of freedom.
exactly. No, here it does. I mean, because in 2 dimension, at least in engaged gravity, the dilaton and the metric are pure gauge, I think. But it has all these scalar fields, which are physical degrees of freedom. I mean, essentially, I'm telling you that all of this is not empty. But yeah, no, it definitely has degrees of freedom. And the fact that you only have a topological term is really due to the fact that you're writing a pseudo-Lagrangian. As soon as you move to a physical action, there is a kinetic term. In this Lagrangian here in the bottom, you have a kinetic term for the physical degrees of freedom. And you have no topological term anymore. Now, there is this thing that once you have like all your dual fields, your whole set, there is nothing really that tells you which ones are the physical ones. I mean, you just have to pick 128 of them to be the physical ones. And depending on which one you pick, you will go to a Lagrangian, a real one, which will have an off-shell symmetry, which is different. Here, the off-shell symmetry is E8, but among all this infinite number of dual scalars, you could say, I don't pick these ones, I pick other ones. And you would go to a physical Lagrangian by rewriting physical plus the self-duality square. That would depend on these different scalar fields, and you wouldn't see E8 anymore. You would, for instance, see SN9 stuff plus some shifts. So that's what I mean. That's picking a frame essentially. That's something I didn't discuss, but the reason why we see E8 in this real Lagrangian is because it comes straight from 3D. But let's say, for instance, you would take 11D subgraph and you would reduce straight 2 dimensions. You would end up on a theory which has just a kinetic term like this with 128 physical degrees of freedom, but you wouldn't see E8 this time. You would see SN9. SL9 times some shift. The SL9 being the symmetry group of the torus on the 9 torus. I mean, that's the.
So, I mean, there are different frames, and only in one frame that you see this infinite dimensional symmetry.
No. So, regardless in which frame you start, meaning in which physical Lagrangian you write, when you take its equation of motions, you can introduce an infinite number of fields, and on this infinite number of fields is this infinite dimensional symmetry realized. But if you start from this pseudo-Lagrangian, which doesn't refer to any particular frame or anything, you can somehow pick which of this infinite number of dual fields, which ones will be your physical ones. Depending on the ones you pick, you will go to a real Lagrangian, which has a different off-shell symmetry. Yeah, I mean, I did it backwards in a way. Yeah. But there is this diagram that I had, but yeah, that's a bit. Yeah, that's if you would just do pure gravity. Pure gravity in 11D. You have, if you reduce on the torus, you just have a metric, you have Einstein invert in 11 dimension, you reduce on the torus, you will get to a 2-dimensional theory with a real Lagrangian, no worries, no anything, and you will have a Lagrangian will have an SL9 symmetry, which is that of the remnant of the diffeomorphisms acting on spine torus. Now, if you first reduce to 3D, you will have an SL8 symmetry on the 8 torus, and then you will also have 8 Kaluza-Klein vector fields. And in 3D, if you dualize the vector fields, you get scalars. So if you do that, you have no more vector fields, you have extra scalars, and there is an enhancement of symmetry in 3 dimensions, which gives you an SN9 as a symmetry. But this SN9 is different from this one. And if you reduce on the circle, you get 2 versions of the theory, of the 2-dimensional theory, which they are the same on shell, but they have a Lagrangian where they have a different SN9, which is realized.
I see.
When you put to this the same story, the SN9 here is in E8 because it comes from the theory, and this one, this SN9 here is not in E8. And so
I see.
with supersymmetry, you would have E8 here, and here you would have another thing like this, SN9 times some other stuff.
So,
and the SO9 group we gauge, just to finish, is inside this SN9.
Okay.
It's not, there is also an SN9, there is also an SO9 inside this one, but if you try to gauge it, it doesn't work. It's inconsistent to gauge this SO9.
Okay.
So that's what I meant by the thing where I cross thing and so on. So that's the SO9 which is in there is in E8, and that's not the one that can be gauged, and the SO9 here can be gauged, and that's the one we're doing by truncating on the 8th sphere.
Thanks.